Good evening to all students. Good evening to all students. Welcome to Pusat Tuition Academy YouTuber collaborated with eDidik Malaysia and Kelab Guru Malaysia. Our slogan is Bermula Percuma, Selamanya Percuma. I'm Teacher Tan from College Matrikulasi Selangor, is the presenter for tonight's session. Before we start the class, I would like to remind all students to be courteous and use appropriate language to give comments in the live chat. Do focus on the contents I delivered and use the live chat to answer the questions I ask. At the end of this class, link for e-sigil will be given and you will have 30 minutes to fill your details. Do remember to use your eDidik email to fill in the form. I believe that all students attending my class are good students and will pay full attention in my class. So without further ado, we shall start the class. So I'm Teacher Tan from College Matrikulasi Selangor. I have 8 years of experience teaching chemistry. So these are my group mate for Pre-U University chemistry group. So they are Cikgu Shannon, Teacher Vivi Lau, Cikgu Marwa, and me, Teacher Tan. So we are led by Cikgu Shannon. And for the Pre-U Mathematics group, we have Teacher Im, Teacher Eileen, and Cikgu Zana. So for Pre-U Mathematics group is led by Teacher Im. And for Pre-U Biology group, we have Cikgu Faiza, Cikgu Fatia, and also Cikgu Naini. So for Pre-U Biology team is led by Cikgu Faiza. And for Pre-U Accounts group, we have Madam Fizi and Cikgu Yati. And for the Pre-U Accounts group is led by Madam Fizi. And now I shall start my lesson for tonight, Reactions Kinetics, focus on orders of reaction. So for the order of reaction, so what is orders of reaction? Orders of reaction basically is referred to the exponents in the red law or red equation. Or we can also say orders of reaction as the power to which the concentrations of reagent is raised to in a red law or red equation. For example, for a reactions where reagents A is converted to product, we can write the red law equation as rate equals to the rate constant K multiplied with the concentrations of the reagent A raised to the power of X. And the X here is the order of the reaction. Is the order of the reaction with respect to the reagent A. For the order of reaction, we can only determine the order of reaction experimentally. Means that from the experimental data, only we can determine the order of a reaction. So for order of reaction, we can determine using initial rate method or even from the unit of rate constant K, or we can determine the rate order of a reactions based on the graph. Based on the graph of reactions rate versus concentrations of the reagent. So basically, this is based on the red law or red equation. Second, we can also determine the order of the reactions from the concentrations versus concentrations of reagent versus time graph. So for this, basically from the graph, concentrations of reagent versus time graph, we can determine the pattern of the half-life. From the pattern of the half-life, then we can determine what is the order of the reactions with respect to that particular reagent. Or we can also determine the order of the reaction based on the linear graph. For the linear graph, so basically is based on the integrated red law equation. Integrated red law for different order will have different linear graph. Okay, and from the from the pattern of the linear graph, we then can deduce the order of the reaction with respect to that particular reagent. Now we move on to look at the first method to determine the order of the reaction, the initial rate method. Okay, so usually for initial rate method, remember, in order to determine the order of a reaction, we need to determine it from the experimental data. So for example 1, you have been given 2 sets of the experimental data. So experiment 1 and also experiment 2. And for this reaction, we only have one reagent, the compositions of the compound A. So only have one reagent. So how could we determine the rate law or rate equation for this reaction? So first, we can write the general rate law equations first. As there is only one reagent, so our rate law can be, the general rate law or rate equations can be written as reactions rate equals to the rate constant K multiplied by the concentrations of the reagent A raised to the power of X. And that X is the order of the reactions that we want to find in this, based on this experimental data. Then we can find our X, the order of the reaction with respect to A, by using the 2 sets of the experimental data. So experiment 1 and also experiment 2. So how can we do this? So we can write the rate law equation for both experimental data, and then we divide the reactions rate for one of the experiment initial rate with another reactions rate value of another set of experimental data. So in these questions, in this example, we have 2 sets of experimental data. So we have 2 initial rate. For experiment 1, 0.68, and for experiment 2, 1.52. So usually what I will be doing is I will use the larger reactions rate value divide with the smaller reactions rate value. So in this example, can you see that the reactions rate for experiment 2, the value is larger than the initial rate for experiment 1 value. Therefore, in order to find X, we use the larger initial rate value. So for the experiment 2, we divide it with smaller initial rate value from the experiment 1. And then when we divide the reactions rate for reactions rate value for experiment 2 with the reactions rate of experiment 1, we also need to divide the concentration. So since we are dividing the data for experiment 2 with the data for the experiment 1, so we need to substitute the concentration of the reagent in experiment 2 into the rate law equations as well, and divide with the concentration of the reagent A in experiment 1, and this will give us this expression for the rate constant. Because the temperature is the same, so can be cancelled out, and then the power is the same, so mathematically we can bring it out, okay, to give us this expression. And then how to find the X value? To find the X value, we can apply logarithm. So we log both sides to give us the S value equals to 2. This S value equals to 2, basically it means that this reaction is second order with respect to the reagent A, with respect to the reagents A. And the second part of the question asks us to find the rate constant. So after we have find what is our X, the order of the reaction, then we can write the rate law or rate equation by substituting the X into the rate law or rate equation. And this will give us the answer So for A, the rate equation or rate law is therefore can be written as rate equals to the rate constant K multiplied by the concentrations of reagent A raised to the power of 2. And in the part B, we want to calculate the rate constant. So how do we calculate the rate constant? So from the part A, we already get the rate law or rate equation. In order to find the rate constant K, we just need to rewrite the equation to give us rate constant K equal to the reactions rate divided by the concentrations of reagent A raised to the power of 2. Then we can choose any set of the experimental data. So in this case, I choose experiment 1 data and then substitute it into the K expression that we write previously. And we can get the rate constant, therefore is equal to the 17 per mole dm cube per minute. How do we get the unit for this rate constant? So basically, reactions rate 0.68, and this is the unit for the reactions rate, divide by concentrations of the reagent A 0.2, and the unit is mole per dm cube, and raised to the power of 2. And this will give us mole squared per dm cube to the power of 6. Okay, and then mathematically, we can cancel, give us mole per mole, and then this will give us dm cube and per minute. Okay, this is how we deduce the unit for the rate constant. Then in the part C, the question asks us to determine the initial rate or the reactions rate when the concentrations of the reagent is 0.4 molar. To calculate this, what we need to do is we just need to substitute the concentration of reagent A into the rate law equation that we derived in the part A to calculate the initial rate when the concentrations of the reagent is 0.4 molar. And the unit for the reactions rate will be equal to the initial rate unit that is being given. Now we move on to look at the second example. In the first example, we only have one reagent. In the second example here, we have two reagents, S2O8 or S2O8 2 minus, and also the iodide ion. Okay, so how do we determine the rate law or rate equations for this reaction and also calculate the rate constant for this reaction? So step number 1, again, we need to write the general rate law equation first. Since we haven't deduced what is the order of the reaction for S2O8 2 minus, so we assume it is X first. And for iodide ion, we also do not know what is the order of the reactions yet, so we assume it's Y first. After we write the general rate law or rate equation, then we can find the order with respect to S2O8 2 minus by making the concentrations of iodide ion constant. So based on the experimental data, which of the two sets having the concentrations of iodide ion remains constant? So based on the experimental data, we can see that experiment 1 and experiment 2 having the concentrations of iodide ion remain constant. So means that in order for us to find X, we need to choose experiment 1 and experiment 2 data. In order to find X, again, we need to use the reactions rate of one experiment data divided by the reactions rate of another experimental data. And usually, I will choose the bigger one as the numerator and the smaller one as the denominator. So the bigger one is the reactions rate for the experiment 2. So I'll put it on the top. Divide by the initial rate for experiment 1. And then we also need to substitute in the concentration for experiment 1 and also experiment 2. Okay, so we substitute for experiment 2. So this is the initial rate value, and concentration of S2O8 is 0.027 raised to the power of x, just like how we write the rate law equation. And the concentrations of iodide ion is 0.036. Divide by reactions rate for experiment 1, and the concentration of S2O82 minus in experiment 1 is 0.018 raised to the power of x, and then the concentrations of iodide ion is 0.036 for experiment 1. So we substitute that into the rate law equation and raise to the power of y. And then can you see that the rate constant can cancel out, and also 0.036 raised to the power of y, we can also cancel them out. So after cancel out, the remain is this term. We can simplify it to get this term and then deduce what is our x. So x therefore is equals to 1. So it means that the reaction is first order with respect to S2O82 minus reactant. So after we have find x, we also need to find the y. So how do we find the y? So in order to find the y, now we need to make sure that the concentration of another reactant, which is S2O82 minus, remain constant. From the experimental data, we can see that experiment 2 and experiment 3 having the concentrations of S2O82 minus remain constant. So means that in order to find y, we need to use the experimental data from experiment 2 and 3. So again, we need to choose the bigger one. So reactions initial rate for experiment 2 bigger, divide with the initial rate of the experiment 2. And then we also need to substitute the concentration for the reactant for experiment. So experiment 3, the concentrations of S2O8 is 0.027, and the concentrations of iodide ion is 0.054. So we substitute that into the rate law equation. And then for experiment 2, the concentration of S2O82 minus is 0.027. So we substitute that into the rate law or rate equation. And for the iodide ion for experiment 2 is 0.036. We substitute that into the equation. And what we get is this term. Okay, since K can be cancelled out, and these two terms are the same, so can cancel out. So we can simplify to get this term. And then we can then deduce our y is equal to 1. Therefore, the reaction is also first order with respect to iodide ion. So after we get the we have found what is our x and y, then now we can rewrite our rate law equation, okay, by substituting in the x and y. Since the x and y are 1 and 1, so therefore our rate law or rate equation can be written as rate is equal to the rate constant K multiplied by the concentrations of reactant S2O82 minus raised to the power of 1 multiplied by the concentrations of iodide ion raised to the power of 1. Then in the part B, we want to calculate the rate constant for this reaction. So how do we calculate the rate constant for these reactions? So again, we rewrite the rate law or rate equation to give us rate constant equal to reactions rate divided by the concentrations of S2O82 minus multiplied with the concentrations of iodide ion. And then we can choose one of the experimental data into the rate constant expression to calculate the rate constant. So in this case, I choose experiment 1. So I substitute the experiment 1 reactions rate into the equation and also the concentration of reactant S2O82 minus and also iodide into the equation to give the rate constant equals to 4.012 times 10 to the power of negative 3 per molar per second. So how do we get this per molar per second? Basically, we can deduce from here. Can you see that? The molar, we can cancel out and then give us per molar per second as the unit for the rate constant. So now we move on to look at how are we going to use the unit of the rate constant and also the graph to determine the order of a reaction. So if the reaction with reactant A converts to product and the reactions is zero order, we can write the rate law equation as rate equal to the rate constant multiplied by the concentrations of reactant A raised to the power of 0 because given zero order. And mathematically, we know that whatever number raised to the power of 0 will give us 1. So we can simplify the reactions, the rate equation as rate equals to the rate constant K. And if we want to plot a graph of reactions rate versus concentration of reactant A, we will get a linear graph like this with the line is equal to the constant of proportionality, the rate constant K. And for the unit for rate constant, for zero order, from these equations, we can see that the rate constant K is equal to the reactions rate if it is a zero order reaction. Therefore, the rate constant will have the same unit as the reactions rate, which is equal to molar per time. Or we can also write it as mole per liter per time or mole per dm cube per time. And the time here can be in seconds, minutes, hours, days, months, or even years. So, and if the reaction is having the reactant A converts to product, we can also write the differential rate equation as rate equal to negative change in concentrations of A with time. And then we can equate the two equations, the differential rate equation, together with the rate law equation to give us this expression. And then we can rewrite the expressions to give us this expression. Then we do the integrations for this equation will give us integrated rate law equation for zero order. So this is the integrated rate law equation for zero order. And for this integrated rate law equation, so I will recommend you to remember it in this form because this form is basically a linear equation form. And remaining concentration A is the Y and minus rate constant is the gradient and T is the X and the initial concentrations of the reactant is the y-intercept. From this, we then know that for zero order, the linear graph will be in this form, where in order to plot the linear graph for zero order based on the integrated rate law equation, So we know that we need to plot concentration of the reagent A versus time. And the initial concentrations of the reagent is the y-intercept, and the gradient of the graph is basically equal to the negative rate constant of the reaction. For zero order, we can also determine the reaction is zero order with respect to the reagent by plotting the graph concentration versus time graph. For zero order, the concentration versus time graph will be linear, will be a linear graph like this. Okay? And then for zero order, we can see that as the initial concentration decreases, the half-life decreases. So this is the pattern for zero order reaction. When we plot the concentration of reagent versus time graph and we deduce the half-life, we can see that the half-life decreases. So why? It is because from the half-life equation for the zero order reaction, we can see that as the initial concentrations decreases, the half-life decreases. It is because for zero order reaction, the initial concentration is proportional to the half-life. Therefore, as the initial concentration decreases, the half-life will decrease. For first order, if the reaction is having reagent A convert to the product, we can write the rate law equations as rate equals to the rate constant. We can write the reactions, the rate law or rate equation as rate equals to rate constant multiplied by the concentrations of A raised to the power of 1. Now raised to the power of 1 because it is first order. So if we plot the reactions rate versus concentrations of reagent A graph, we will get a directly proportional graph, because from this equation, we can see that the reactions rate is directly proportional with the concentrations of reagent A. So this is the pattern for the first order graph. So for the unit of the rate constant for first order reaction, the rate constant unit will be per time. And the time again can be second, minute, hours, years, months, or even months. Okay. So if we write the differential rate equation for this reaction, so the rate is equal to the negative change in concentrations of reagent A to the change in time. Okay, so the negative here basically represent that reagent. As the reactions proceed, the concentrations of reagents will decrease with time. By equating the rate law equation, rate law or rate equation with the differential rate equation, then we get this expression. When we rewrite these two equations, we can get this expression. And when we integrate these two equations together, we will once again get the integrated rate law equation. But now, this is for the first order reaction. For the first order reaction, the integrated rate law equation is ln concentrations of reagent A equals to the negative rate constant multiplied with time plus ln initial concentrations of the reagent A. Okay, and then from this equation, again, this is linear equation. So ln A is the y, and negative rate constant is the gradient of the graph, and then t time is the axis, and ln initial concentrations of reagent A is the y-intercept. So based on this integrated rate law equation, then we know that the linear graph that we need to plot is long concentrations of A versus time. With long initial concentrations of A is the y-intercept, and the gradient of the graph is equal to the negative rate constant of the reaction. So for the first order reaction, we can also determine it from the concentrations versus time graph. So for the first order reaction, the first order reaction, when we plot the concentrations versus time graph, we will get a curve like this. And when we determine the half-life, we can see that for the first order reaction, we get the half-life constant. Okay, it is because for the first order reaction, so the half-life is equal to the ln 2 divided by rate constant K. And can you see that the half-life for first order reaction is independent from the initial concentration. Therefore, as the initial concentrations decreases, the half-life for the first order reaction is still remain constant. So must remember that for the first order reaction, the half-life is constant because for the first order reaction, the half-life is independent from the initial concentration of the reagent. So now, shall we stop for a while for a break?
Semua sekolah ditutup hingga cuti akhir tahun 17 Disember 2020. Anda tak cukup bahan? Tak ada rujukan? Tak faham? Anda nak tuition tapi PKP? Jangan risau, kami di Akademi YouTuber dengan kerjasama Kelab Guru Malaysia dan e-Didik Malaysia mengadakan kelas tuition online. Semua peringkat ada, semuanya secara percuma. Video PDPC pun ada. Apa ditunggu lagi? Layari www.academyyoutuber.com. Dibawakan kepada anda oleh Akademi YouTuber.
So now shall we continue with the class? So just now I have covered the first order half-life. So now we move on to look at the second order. So if the reaction is second order with respect to the reagent, and the reaction is reagent A convert to product, then we can write the rate law or rate equation as rate equals to the rate constant multiplied with the concentrations of reagent A raised to the power of 2. Here, raised to the power of 2 because it is second order. And when we plot the graph of reactions rate versus concentrations of reagent A, we will get a quadratic graph. And the unit for the rate constant K is per molar per time. Okay, so how do we get this per molar per time? Again, this is our rate law or rate equation. So rate is equal to rate constant multiplied by the concentrations of reagent raised to the power of 2. So now we want to find the unit for the rate constant. So therefore, it is equal to the rate divided by the concentrations of reagent A raised to the power of 2. And the reactions rate, usually the unit will be, must remember, reactions rate basically refer to the change in concentrations over time. So the unit will be concentration per time. And the time again can be second, meaning hours, months, or years. Okay, divide by, so concentrations of reagent, molar raised to the power of 2. So cancel, we get the unit for the rate constant, therefore as per molar per time. Okay, and then for the differential rate equation, so if this is our reaction, so for differential rate equation, we can write the expressions as rate equals to negative change in concentrations of reactant A over change of time. Negative because, again, A is reactant. Therefore, the concentrations of A reactant will decrease as the reaction proceeds. When we equate the two equations together, we get this expression, and rearrange, we get this expression. And then when we integrate the equations, we get this equation. And this equation is the integrated rate law equation for second order. Again, this integrated rate law equation, I will suggest you to remember it in the linear graph form. Okay, y equals to ms plus c, where your y is equal to 1 over concentration of your reactant A, and the gradient of the graph is equal to the rate constant, and the x-axis is the time, and the y-intercept is 1 over initial concentrations of the reactant. And then from this integrated rate law equation, we know that the linear graph will be 1 over concentrations of reactant A versus time, with the 1 over initial concentrations of A as the y-intercept, and the gradient of the graph equal to the rate constant. For second order reaction, we can also plot the graph concentrations of reactant versus time to determine that the reaction is second order. Okay, after we have plot the concentrations versus time graph, so basically what we need to do is we determine the half-life. And for the second order reaction, we can see that the half-life increases. The half-life increases as the initial concentrations decreases. So why? It is because from the half-life equation for the second order reaction, we can see that the initial concentration is inversely proportional to the half-life. Therefore, as the initial concentrations decreases, the half-life increases. Okay, so this is the pattern for the second order reaction. So with this, we can then summarize the order of the reactions in this table. For zero order, the unit for the rate constant is molar per time. Okay, and for the first order is per time, and for second order is per molar per time. Okay, so sometimes in the question, not given what order. So if not given which order, we can also use the unit of the rate constant to determine the order of the reaction. And for the zero order, the rate law or rate equation is equal to the can be written as rate equals to the rate constant. And when we plot the graph of reactions rate versus the concentrations of reactant, we will get a linear graph like this. And for first order, the rate law or rate equation can be written as reactions rate is equal to the rate constant multiplied by the concentrations of reactant A raised to the power of 1. 1 because first order. And when we sketch the graph of reactions rate versus concentrations of reactant A, we will get a directly proportional graph. For second order, the rate law or rate equation is can be written as rate equals to the rate constant multiplied by the concentrations of A raised to the power of 2. And when we sketch the graph of rate versus concentrations of reactant A, we will get a quadratic graph. Okay, so again, raised to the power of 2 because second order. For the integrated rate law equation, for zero order, this is the integrated rate law equation. Again, always suggested to remember it as linear equation form. so that you know what graph to plot. So from this linear equation, we know that the y-axis is concentrations of reagent A and the x-axis is the time. And we get a linear graph. And for the first order reaction, integrated rate law equation is long concentrations of A equals to negative rate constant multiplied by time plus long initial concentrations of reagent A. Okay, again, remember it in linear graph form so that you remember what graph to plot. From this linear equation, we know that the y-axis is long concentrations of reagent A and x-axis should be the time. Okay, and for the second order, so this is the integrated rate law equation. Okay, also remember it in the linear graph form, so linear equation form, so y equals to ms plus c. And from the equations, we know that our y-axis should be 1 over concentrations of A and time will be x axis. Okay, and this should be the graph. So for half-life, doesn't matter is 0 first or second order, we need to plot concentrations versus time graph. For 0 order, must remember that when the initial concentrations decreases, the half-life decreases. Okay, because the initial concentration and the half-life is directly proportional. And for the first order, we still plot concentrations of A versus time graph, but now for the first order reaction, the half-life is constant. Okay, so the half-life is constant, so means that when the initial concentrations decreases, the half-life is still remain constant. So this is the pattern for the first order reaction. For second order reaction, we still plot concentrations of reagent A versus time t. Okay, but for the second order reaction, as the initial concentrations decreases, we can see that the half-life increases. Must remember, this is the pattern for the second order reaction, where the initial concentration is inversely proportional with half-life. So when the half-life, the initial concentrations decreases, the half-life will increase. So far, any question? Okay. So if no question, then we move on to look at question 1. So for question 1, okay, so this question asks to to sketch the graph of concentrations versus time. And from the questions, the questions mentioned that the reaction is first order with respect to both propanol and the acid. Both propanol and the acid is first order, but it is 0 order with respect to iodine. So this is 0 order. And asking us to plot the concentration versus time graph. So for propanol, remember it's first order. So when plot the concentrations versus time graph will give us a curve. And then remember, for the first order reaction, if we deduce the half-life, okay, so the half-life is constant. That is the trend or pattern for the first order reaction. And for the acid, concentrations of acid against time, so just now mentioned in the question, is also first order. If first order, when we plot concentrations versus time graph, it will be a curve. So again, if we deduce the half-life, when we deduce the half-life, because this is the first order reaction, so the half-life again will be constant, okay, because that is the pattern for first order reaction. And for iodine, questions mentioned it is zero order. So when it is a zero order reaction, when we plot the concentrations versus time graph, it will be a linear graph. It will be a linear graph like this. Okay, so it will be a linear graph like this. Now we move on to look at question number 2. Okay, so in question number 2, again, the question asks to use a graph to determine the order of the reaction. So how to determine the order of reaction? Again, we need to determine it based on the experimental data. And for this question, they want you to use the experimental data, plot a graph, and from the graph, deduce the order of the reaction. So what graph should we plot? For this question, not mention linear graph. So means that we can plot concentration versus time graph. Okay, we can plot concentrations versus time graph like this. And then from the concentrations versus time graph, so how can we tell which order is the reaction with respect to sucrose? So we need to deduce the half-life. So how do we deduce the half-life? So we need first find the initial concentration. So the initial concentration is given in the question. At time 0, so this is the concentrations of your sucrose. So this is the initial concentration. And then in order to deduce the first half-life, we need to deduce the half concentrations, half initial concentration, and the half initial concentration is 0.158 molar. And from the graph, it is here, and that is equal to 190 minutes. 190 minutes. So means that the first half-life is equal to 190 minutes. And then we deduce the second half-life. So in order to deduce the second half-life, the half concentration, we need to divide by 2 again to give us the 1/4 concentration equal to 0.079 molar. And from the graph, 0.079 molar is at the time 380 minutes. And to deduce the second half-life, basically 980 minutes, we need to minus with 190 minutes to give us the second half-life, which is equal to 190 minutes. And can you see that the half-life is constant? The first half-life and the second half-life are the same. So means that the half-life is constant. So if the half-life is constant, means that the order of the reaction is first order. Means that the reaction is first order with respect to the reactant sucrose. Okay, since the half-life is independent from the initial concentrations of sucrose, therefore the reaction is first order with respect to sucrose. So, and then the part B asks us to determine the half-life of the reaction. So we have determined from the graph, so the half-life of the reaction is equal to 190 minutes. And then the part C asks us to deduce the rate constant. So we just need to use the half-life equation for the first order. And then we rewrite the equation to equate it to the rate constant. And then substitute the half-life into the equation to give us the rate constant for this reaction equal to 3.648 times 10 to the power of -3 per minute. Now we move on to look at the last question, question number 3. So for question number 3, the question asks us to use linear graph. So remember, linear graph means that we need to use the integrated rate law equation, because the integrated rate law equation will give us the linear graph. So in this question, ask us to use the linear graph to determine the order of the reaction. And then from the graph, we determine the rate constant and then calculate the initial concentration, initial rate when the initial concentration of the reactant NO2 equals to 0.2 molar. So how do we do this question? Because the question asks about linear graphs, so means that we need to plot 3 graphs. We need to plot 3 graphs. So the first one is based on the integrated rate law equation for 0 order. So remember, for 0 order, we need to plot concentration versus time graph. And for this, we get a curve. So if we get a curve, means that the reaction is not 0 order. It's not 0 order. Okay? And then we also need to plot long concentrations of reactant NO2 versus time graph. And also we get a curve. So if we get a curve, means that once again, the reaction is not first order. So we also need to plot 1 over concentrations of reactant NO2 versus time graph. And now we get a linear graph. We get a linear graph. So when we get a linear graph, so basically it means that the reactant is that particular order. So if we get 1 over concentrations of reactant versus time graph linear, means that the reaction is second order with respect to the reactant NO2. It is second order. So this is how we use the linear graphs to determine the order of a reaction. We need to plot all the 3 integrated rate law graphs. So for concentrations versus time, long concentrations versus time, and 1 over concentrations of reactant versus time, to see which graph give us linear graph, and the linear graph will tell us the reactant is the reaction basically is which order with respect to the reactant. And for our examples here, we get 1 over concentrations of reactant NO2 versus time, a linear graph. So means that the reaction is second order with respect to the reactant NO2. Okay, so after we have determined it is second order, we then can determine the gradient of the reaction. We can determine the rate constant of the reaction. So from the rate law equation, okay, we are having the 1 over concentrations of reactant versus time graph. So means that in order to determine the rate constant K, we can deduce it from the gradient of the graph. We can deduce it from the gradient of the graph. And the gradient of the graph basically is equal to the rate constant of the reaction K. And how do we determine the gradient of the graph? So basically we can draw a big triangle, okay? And then the rate constant is determined to be 10.14 per mole per second. And then in the part C, we want to calculate the initial rate if the initial concentrations of NO2 is 0.2 molar. Okay, so we already know that this reaction is second order. It is second order with respect to the reactant NO2. Therefore, we can write the rate law or rate equation as rate equals to the rate constant K multiplied by the concentrations of the reactant NO2 raised to the power of 2, because we already determined it is second order. And then by substituting the rate constant that we deduced before into the reaction and the initial concentrations given into the equation, then we can determine the initial rate if the concentrations of NO2 equal to 0.2 molar as 0.4056 molar per second. So basically, that's it for my today's class. So, any question? Oh, so, okay. So, okay, so the question from Jiajun. Okay, if got 1.98 can round off to 2, yes. Okay, so the order, we can round that to 2. Okay, so any other question? Okay, so if no question, then okay. So if no question, then thank you for being with me until the end of the class. So before we go, okay, so please close your live chat and click on the subscribe button until it turns gray. And if you like what you learned tonight, do click like and share with your friends in your social media, such as Facebook and Instagram, so that more students can be benefited from my sharing. So do type done in the live chat before the certificate link is given as the token of appreciation for you to attend my class. Do use the EDD email to access the form and access the access code. Okay, is hashtag class RU EDD. Okay, and also don't forget to also get the online tuition timetable from www.academyyoutuber.com. So do help to spread the news to of free tuition class with your teachers and friends, and hope that the classes like this can benefit more students. So thank you all, and see you next time. Okay, so before I go, okay. So this is the code. And the link. Okay, so the link is. So this is the link. So you have 30 minutes to fill in the form. Okay, so that's it from me for tonight.
Tuition online percuma. Tuition online percuma. Layari www.academyyoutuber bagi mengikuti tuition online secara percuma. Prasekolah, sekolah rendah, sekolah menengah, semua ada di Akademi YouTuber. Rujuk jadual di laman
dibawakan kepada anda oleh Akademi YouTuber.